This is a lecture on chapter 1.7, which involves combination of functions and composite functions. So combination of functions means combining two or more functions. And composite functions refer to when we use one function as an input to another function. So we take g of x and we use that, the value of g of x, to become an input into an, another function, which is f of x. So we will be working through some examples. We will be talking about those in more detail. So what we are going to cover in chapter 1.7 are these topics here. First, we are going to talk about finding the domain of a function. That means all the set of values that can be input into a function, into a given function. Then we are going to talk about combining functions using the algebra of functions. And the algebra of functions is nothing but addition, subtraction, multiplication, and division of functions. All right, we use those operations to combine functions. And then forming composite functions, which means we use uh, one function to become the input to another function and then evaluate it perhaps. All right, so we'll go into details on that. Determine the domains for the composite functions and then write functions as composition. So first, let's talk about how to find a function's domain, how to identify the set of values of x that can be input into a function. I'm going to first read through the verbiage here and then I will explain it in more simple terms. All right, so if it says here, if a function f does not model data or verbal conditions, its domain is the largest set of real numbers for which the value of f of x is a real number. Exclude from a function's domain real numbers that cause division by zero and real numbers that result in an even root, such as a square root of a negative number. Essentially, what this means is that you can input any real number for x into a function as long as that value of x produces a real number for y. Keep in mind, y and f of x are the same things, all right? Y and f of x are used interchangeably. So as long as the x value that you input into a function produces a y value, an output value, which is also a real number, it can be included in the domain of that function. All right. Now, let me just write it down quickly, what that means, or summarize that. It means that x can take any real number. It can take any real number as an input to a function, as long as it produces a real number for the y value. For the y value. All right. So one other thing though is sometimes in real life, if we are modeling data in what that means is if it is an application, if it's a word problem which is a real life based problem, then there will be some natural constraints into the values that we can input into a function. For example, let's say we want to, we have a function, all right, we have f of x, where x is the age and the y value, all right, x is the age, and this f of x produces height, all right, given by, and I'm just making up this equation, this is a meaningless and not a true function for age and height, but let's say there is a function which is f of x equals 19 plus 2x, where x represents age and f of x represents height. So the y value represents height and x represents age. All right. So if we want to study the domain of this function, all right, think about it. Age cannot be a negative value. All right. Normally, this is a linear function. We can see that 19 plus 2x. Normally, if this was not a word problem with age and height, then we could input any value for x from negative infinity to positive infinity. We could include negative values, we could include fractions, we could include decimal values, we could include anything, any number from negative infinity to positive infinity. However, when our x value represents a real life variable like age, all right, age cannot be a negative value. All right, age can only start from 0 years and then 1, 2, 3, 4, and then even as we go up higher, age will probably stop at, depending on the lifespan, we can go maybe as far as 100, 105 years maybe, or a little more, I don't know. But we cannot input, it doesn't make sense to include negative values in x. So if it is a real life based problem, application problem where we are trying to model data, then there will be some natural constraints on the domain of x, on the domain of the function, the x values of the function. All right, so that is what the first line of here in this definition is saying. If a function f does not model data or verbal conditions, as long as it's not a application-based problem, x can take any value from negative infinity to positive infinity as long as it produces a real number for y. All right. However, there are some situations where the operation will not allow a real number to be produced, and you probably already know that. One of them is division, right? We cannot divide uh, any number by 0. Division by 0, all right, it produces an undefined value. It will not give us a real number. So if we have a function where x is in the denominator, or let's say f1 divided by x plus, well, not, yeah, 1 divided by x plus 1. Let's say we have a function which is 1 divided by x plus 1. We always have to remember that we cannot input a value of x which will make the denominator equal to 0, because 1 divided by 0 will not produce a real number for y. It will become an undefined number, so we have to make sure we exclude, all right, in this case -1, a value of -1 for x would make the denominator equal to 0, correct? So we have to, by all means, exclude that from the domain. All right. Another situation where it will not produce a real number is the even root of a negative value, And what even root means is, oh, sorry, negative value. So what even root means is It could be a square root. So square root of -4 doesn't exist. All right. It produces what is called an imaginary, not an undefined, but it's called an imaginary number. It's not a real number, imaginary number. All right. So we cannot by any means have a negative number under a square root or a fourth root or a eighth root or any even root, because there's no number, there's no real number which when multiplied by itself twice will produce a negative number. For example, -2 squared is +4. +2 squared is also +4. There's no way we can think of a number which when squared is going to give us a -4. It only exists in imagination. So that's why it's called an imaginary number. So when the function has a square root or any even root, we have to make sure that what we have under the radical sign is not a negative value. It can be 0 or greater than 0, but not a negative value. Now, if it is an odd root, like a cube root or fifth root or seventh root, the radicand can be a negative value. It is not a problem. All right. However, it will still produce a, for example, the cube root of -8 is -2, right? But only when it's an even root, we have to make sure that the radicand is never negative. It has to be a value greater or equal to 0. All right, it can be 0 or it has to be greater than 0. So we have to exclude all values of x under the radicand which will make the radicand. So if we have something like square root over x minus, I don't know, I'm just making up here, x minus 5. All right, we have to make sure that x minus 5, we cannot input, we have to make sure that we don't choose a value for x which will make x minus 5 a negative value. All right, so if x is -6, then -6, -5 becomes a -11, and oh, there's a problem. All right, we have to exclude -6 from the domain. Likewise, any value of x, and the way we do it is we just take x minus 5, okay, and see what values x minus 5 less than 0 and solve for x and exclude those values. So we will go through some examples. In the next slide we do an example of division of rational function, but later on we will also do one for even roots, how to find the domain of in even roots. Now this is an example of finding the domain of a function. So the function that's been given to us is a rational function which involves a denominator, and x is in the denominator, it's part of the denominator. It's in the numerator too, but it's x is also in the denominator, and that is what causes the problem, because we cannot input any value of x in this function which will make the denominator equal to 0. When we evaluate x squared minus 49, the denominator should not amount to 0. 0 in the numerator is just fine, because 0 divided by any value is 0, and a 0 is a real number. The problem is only when x is in the denominator, we cannot input a value of x that will make this whole x squared minus 49 equal to 0. All right. So we need to exclude those values of x when we define the domain. So let's see how to work through that. They've given us the solution, but it says because division by 0 is undefined, it will not produce a real number uh, for y, we have to exclude those values. All right, so all you do is take your x squared minus 49, whatever is in the denominator, and just the denominator. All right, just totally ignore the numerator, because the numerator is not a problem here. It's the denominator that's the problem. So take x squared minus 49, make it equal to 0, and solve for x. Find values of x which will make the whole expression equal to 0. So the way you can do the solving in different ways. You can use you can factor x squared minus 49 and make each factor equal to 0, and then use the zero factor property to find values of x. But the way they've done it here is they've moved the minus 49 over to the other side, and we have x squared equals positive 49, and then they've taken the square root of both sides. All right, to get rid of the square on the x, they've taken the square root of both sides, but we have to make it a plus minus square root of 49. Okay, and then we get x equals plus minus square root of 49, therefore x is plus minus 7. So that means those two values of x must be excluded from the domain of this function, because if we input minus 7 into x, then minus 7 squared is positive 49. 49 minus 49 will make the denominator equal to 0. Likewise, if it's positive 7, 7 squared is 49. 49 minus 49 will make the denominator equal to 0. So somehow we have to, or we must exclude those values. So the way we write it in interval notation is we start from minus infinity. So x can be any value all the way from negative infinity up to as close as you can get to negative 7 from the left side. All right, so if I draw my number line here, okay, I'll just draw a figure here. Let's say these are my x values, number line with 0 being in the middle. All right, just a second. And let's say negative 7 is, I don't know, somewhere here, and positive 7 is on the right hand side of 0. So what it's saying is you can pick any value of x, input any value of x into this function, and get as close as possible to negative 7, but it cannot be negative 7. All right, you have to exclude. It cannot be exactly negative 7, but from the left hand side you can pick any value starting from negative infinity all the way to negative 7, and this round bracket next to on the right hand side of negative 7 says that negative 7 is excluded. All right, do not put a square bracket. Make sure you're putting a round bracket, because round bracket suggests exclusion. So we are getting as close as possible, as close, uh, micro millimeter close to negative 7, but we cannot choose negative 7 as our value to input into the function. And once we cross this negative 7, all right, once we cross negative 7, we can continue, all right, all the way to as close as possible to 7, but we cannot hit 7. All right, 7 must be excluded. So what it's saying is, the way we write it is, we start from negative infinity to negative 7, and then union, again, round bracket suggests that negative 7 is being excluded, but then we can start immediately with the closest value of negative 7 to the right of negative 7, and go all the way to positive 7, all the way to positive 7, but we cannot touch 7. Okay, so 7 is excluded, and so we have a round bracket to the right of 7. And then again the union, because once we cross that 7, all right, that once we cross the 7, we are good for the rest of the numbers all the way up to positive infinity. All right. So that's why they have union 7 to infinity, and all through we have round brackets. All right, we always put round bracket next to it, negative infinity, because negative infinity is not a number, so to speak, and same with positive infinity. All right, it just says that you can go as far as you can with the numbers. We'll now talk about the combination of two or more functions using the algebra of functions. Now we combine two functions using the arithmetic operations, which are addition, sum, subtraction, difference, product, meaning multiplication, and quotient implies division. So the sum, f plus g, so we can take two functions and add them. We can take two functions and subtract them. We can multiply two functions, and we can divide two functions. And when we combine the functions in this way, a completely new function is produced. All right, so let's say we are combining f of x with g of x. The result is another function, maybe h of x. All right, now that new function, which is formed by combining two functions, will have its own domain, and its domain will be, the new function's domain will be the common domain between f and g. In other words, we look at the domain of f of x, we look at the domain of g of x, and then we look at what is common. What is the common domain between the two? And that common domain is going to be the domain of the new function that we obtain, maybe h of x or whatever, after combining f and g. All right, now this notation here says the domain of f of x, d sub f, and then on the other side we have the domain of g, and this downturned u is actually set notation. It means intersection. All right, intersection means the common, it refers to the commonality. All right, let me write that, intersection. So let's say we have a domain for f. All right, this implies f, and then there is a domain for the function g. Okay, there's a domain for the function g. Now the new function, let's say h, which is formed by combining f and g, is this portion of the function, the common set of domain values between f and g. All right, so we exclude the domain values of f which are not same as the domain values of g. Right, we'll talk about in more detail about how to find the domain of the combined function, but let's look at a mathematical representation of the combination. So the way we write the sum of functions is f plus g and then x. All right, so f plus g is within one bracket and then of x equals f of x plus g of x. So we take the function f of x, we take the function g of x, and we will just add them. Same with difference, instead of adding we will subtract f times g. So again fg within one bracket and x in a separate bracket next to it equals, just take your f of x function and multiply it by g of x. All right, but it'll be algebra, all right? It'll not necessarily be a numerical answer. It'll be another function that you're producing. Quotient implies division, so f divided by g of x. So f of x divided by g of x. However, keep in mind that in division we cannot have a 0 in the denominator, so this will only work provided g of x, the denominator, is not a 0. The denominator does not give a 0. All right. So in the next slide, we will look at an example of the algebra of functions. Let's look at this example where they are combining two functions, f of x equals x minus 5 and g of x equals x squared minus 1. And they want us to find f plus g of x and also the domain of the new function that we find. All right. So remember, we discussed in the previous slide that f plus g of x is the same as f of x, taking whatever f of x is, which is x minus 5, and adding g of x, the function g of x, the equation of it, x squared minus 1, and adding them up. So if this were minus, then we would have to subtract. If this were a product, if this were multiplication, this instead of a plus, this would be multiplication, and same for division. All right. So I'm going to work on the side, although they have worked it, but I think it's easier to follow if somebody is working through step by step. So it's f of x plus g of x, right? So let's look at the function for f of x. It's x minus 5, right? That's f of x. And then plus, because it's a sum, so plus, what's the function for g of x? It's x squared minus 1. All right, so this is just simple algebra. Add the two expressions here. So we have x minus 5, I'm taking off the brackets now, plus x squared minus 1. All right, and now we have to combine whatever is whatever can be combined. All right, so we have an x. Do we have another term with x in it? Let's see. We have a minus 5, which doesn't have an x. This is an x, but it's an x squared. We cannot combine x with x squared. In order to combine two terms, it has to be the same variable or raised to the same power. This is x to the 1, this is x squared, so we cannot combine them. This is not combinable. And then we have minus 1. So x cannot be combined with anything. So I'm just going to write it as x, all right? And then we have minus 5 and minus 1. Minus 5 and minus 1 can be combined. Minus 5 minus 1 is minus 6. And x squared is by itself. We cannot combine it with anything. And now that we have x minus 6 plus x squared, a polynomial, a trinomial expression, always make it a habit of rewriting the polynomial or any polynomial in order of their exponent from highest to lowest. All right, so here we have x squared, which is the highest power, so x squared plus x minus 6 is our new function that we obtained by combining f of x and g of x. All right. So now the next part says find the domain of this. All right. So the domain of f of x, this is a linear function. So the domain of f of x will be negative infinity to positive infinity. Remember, in a linear function, you can input any value for x all right, from negative infinity to positive infinity, and it will always produce a real number for the y value. G of x is a quadratic function, x squared minus 1, but in a quadratic function too, we can input any value for x to produce a real value, real number value for y. So f of x and g of x both have the same domain, minus infinity comma infinity for both. Therefore, the new function, all right, which is f plus g of x, will have that the common domain of minus infinity comma infinity. All right. Let's talk about the composition of functions now. Previously, we talked about the combination of functions, which was addition, subtraction, multiplication, or division. That's how we combine functions. But here, this is something different. This is called the composition of functions. And what is it? The composition of the function f with g is denoted f, and then there's a hollow circle between f and g. It is defined by this equation: f composition g of x equals f of g of x. So let me remind you, this hollow circle does not indicate multiplication. We are not multiplying two functions here. What we are doing is we are creating composite functions, and let's understand how we do that. What we are doing here is we are taking g of x, the function g of x, and using it as an input to the function f and evaluating f of g of x. All right. Again, we will go through an example in the next slide of this, how to work this. The domain of the composite function f composition G is the set of all x such that x is in the domain of G and G of x is in the domain of x. Okay, so again, don't worry if it seems a little bit abstract. Let's go on to an example and it'll be easier for us to understand. Let's see how they've worked out a composite function in this example. It says given f of x equals 5x plus 6 and g of x equals 2x squared minus x minus 1, find f composition g of x. So remember, in order to work a composite function, what we do is we take the second function g and use it as an input to the first function. So our function is 5x plus 6. So what does that mean? That means we have to take this entire expression of g of x, and substitute that into x, right? That's how we evaluate a function. How would we evaluate, let's say, f of 2? All right. To evaluate f of 2, all we would do is 5. We would substitute x with 2. So 5 times 2 plus 6, and that would give us 10 plus 6, 16. Right? That would be f of 2. Now here, what we are doing is we are inputting, all right, we are inputting this entire expression into x. All right, so it's going to be, let's see what they've done here. It's going to be f of 2x squared minus x minus 1. All right, so instead of just 2 or 3 or a numerical value as an input, we are inputting the entire expression. So it's some algebra, not too hard, but it's some algebra that you will be working through here. All right, so our f of x was 5x plus 6. Now, I always like to work on the side instead of just skimming through the, all right, so our f of x was 5x plus 6. All right, so when we do f of g of x, we have to substitute 2x squared minus x minus 1 into x. We have to replace x with 2x squared minus x minus 1. So I'm going to write it as 5 times 2x squared minus x minus 1. And don't forget the plus 6 because that's a part of the f of x function, plus 6. All right, you see what I did here? I replaced the x in the 5x plus 6 with whatever expression g of x had, which was 2x squared minus x minus 1. And now it's just plain algebra. We have to multiply all the terms inside the brackets, distribute 5 and multiply all the terms inside the brackets with and rewrite this, right? So 5 times 2 is 10x squared minus 5 times x minus 5x, and 5 times negative 1 is minus 5 plus 6, correct? And now we see what we can combine. It's 10x squared, right? We cannot combine. We don't have another term with x squared in it. So we just have to write it as 10x squared minus 5x. There's no other term with an x in it, so minus 5x, but we can combine. Minus 5 plus 6 is positive 1, all right? And that's the new expression. All right, and that's what they got here too, right? 10x squared minus 5x plus 1, and that's what f of g of x is. So when we formed the composite function here, we came up with a totally different function, 10x squared minus 5x plus 1. All right, now we could also be asked to do g of G composition f of x. All right, so in that case, what we'll be doing is we will be inputting f of x, all right, f of x in this case will become the input into g of x. So that means we have to take 5x plus 6 and input 5x plus 6 wherever x is, into x squared, into this x, and then do the algebra. Okay, so let's go to the next slide and they will talk about how to find the domain of the composite. Here we are going to talk about excluding values from the domain of f composition G, also referred to as f circle G of x, which is equal to f of G of x. Right, now here in this presentation they talk about excluding values, which will be a different function. Not all compositions will need the domain to be excluded, right? For example, in the previous example, where f of x was a linear function and g of x was a quadratic function, f of x had a domain. Individually, f of x had a domain minus infinity to positive infinity, right? Any linear function has a domain from minus to positive infinity. Quadratic functions too, they will have a domain minus infinity to positive infinity. Therefore, the resulting composed function would also have a domain of minus infinity to positive infinity. Now, here there will be, of course, certain cases where we will need to exclude values from the domain of the newly formed function. So let's read what they say here. The following values must be excluded from the input of x. If in a particular function we see that x is not in the domain of g, then it must not be in the domain of the newly formed function either. Okay, so in the case of, we studied that in the case of division, as well as in the case of even roots, we cannot input certain values of x which would make the denominator equal to 0 in division, or if it's a case of even radicals, then we cannot input, we have to exclude x values which would make the radicand negative value, correct? So that's what they are referring to, those kind of functions. So if there are some x values which cannot be included in the g of x function, which are not in the domain of g of x, then they should not be in the domain of the newly formed function either. And then any x for which g of x is not in the domain of f must not be in the domain of f composition g. So let's go through an example, and it'll probably be easier to explain through the example. Now here's an example of forming a composite function and finding its domain. As you will note, we are given two functions, but both the functions are rational functions. They involve division, and the domain restriction usually happens when we, in the case of division or radicals. Okay, so that's why they have given us, they worked out an example which involves division in its functions. So we have f of x equals 4 divided by x plus 2, and g of x equals 1 divided by x. Find f composition g of x. So when g comes after f, whatever function comes after x, that is the function which is input into the first function f. Okay, so we have to rewrite f composition x as f of g of x, which means whatever expression g of x is, 1, which is 1 divided by x, has to be input into this function. So wherever there is x in the first function, there we have to substitute the x with 1 over x, f of g of x. And that's what they have done here. So 4 is in the numerator, there's no x there, so there's no question of substituting anything here. In the denominator, we have x plus 2. So into the x, we substitute 1 divided by x, and then don't forget the plus 2. Okay, and then the way they have worked through the algebra is they've got rid of this x in the denominator, and the way you get rid of the denominator of a particular denominator is to take the LCD, the least common denominator, and multiply all the terms by that least common denominator. So over here, when we want to get rid of the x, this is our denominator we want to get rid of. So this is, in this case, the least common denominator is x, right? So let me just use my pen here. All right, so we have 1 divided by x plus 2. Okay, so x is what we want to remove from we want to get rid of the denominator. So what is the common denominator between x and 1? All right, 2 has a denominator of 1, although it's not visible. Between x and 1, the LCD, least common denominator, is x. So what we do to get rid of x in this denominator is multiply all the terms in the expression by x. So we take 4, multiply that by x, then this is a term, right? 1 divided by x is a term. So 1 over x multiplied by this x, which is the LCD, and then plus 2, multiply the 2 by x as well. All right, so basically you are multiplying all the terms by x. All right, so what do we get here? This x and this x divides. So we've got rid of the denominator in the denominator. And what are we left with? We are left with 4x in the numerator. So this is 4x. And then 1 plus 2x. Okay, and that's how they got this answer. All right, I just wanted to work through a little bit. I thought it would be easier for you to follow if I showed you exactly how they got from here to this final answer, because I felt it was not too clear what the steps were. All right, this multiplying by x divided by x could have been a little bit difficult to follow for a few of you. That's why I explained it. But let's see now. So far we've just found the new composed function. We still need to find the domain of this new function. All right. Now this is where we determine the domain of the composite function that we obtained in the previous slide. All right, so if you remember, the composed function f of g of x was 4x divided by 1 plus 2x. Okay, so the resulting function also is a rational function, right? This is also a rational function. Now the rule is that to create the domain, to determine the domain of the new function, newly composed function, we first have to see what the domain of the input function was. In this case, the input function was g of x. All right, were there any x values that we had to exclude in just the g of x function? All right, yes, right, we had a x in the denominator. X cannot be a 0, so 0 had to be excluded. So we have to figure that out first. In the input function, were there any exclusions in the domain? So one, x equal to 0, we are just trying to figure out the exclusions, and then we will set up the domain in interval notation with incorporating the exclusions and everything. But now let's just figure out the exclusion. So in g of x, and let me just, so first we consider the input function, the function that we input into g of x. So in g of x, all right, x equal to 0 excluded. Okay, we could not uh, use x, an x value of 0 in the domain of g of x. All right, so we have to make sure that 0 gets excluded from the newly formed function as well. All right, and then secondly, so that's one exclusion. And secondly, we take the denominator of the newly formed function and see what x value must be excluded so that the newly formed function's denominator does not become a 0. All right, so let's look at that. Remember how we learned to work through finding the x value to exclude. All we do is we take the denominator 1 plus 2x, make it equal to 0, and see for what value of x will 1 plus 2x, this whole expression, become a 0. All right, so in other words, we are solving for x here. So step by step, this is 2x equals -1, so x will be -1/2. So that's going to be the excluded value. Again, this is the excluded value from which function? From f of g of x function, the newly formed function here, this function. So we have to exclude 0 because that had to be excluded in the original g of x function, which was an input into f of x. And secondly, we also have to see what needs to be excluded in the newly formed function. Okay, so there are two functions that we are looking into, the inputted function domain as well as the newly formed function domain. So you see the way they write it here. So let's read through the solution. It says for g of x, x should not be a 0, right? X, that's exclusion. X cannot be a 0. And for the newly formed function, x not equal to -1/2, that means x cannot be -1/2. Other than that, any value can be in the domain of this newly formed function. So the way we write it is start from -∞, comma -1/2, always the lower value first, so -1/2 is less than 0, so start with that, and then union. Okay, this upturned U suggests union in interval notation, and then again round brackets from -1/2, comma, we go all the way up to 0, but 0 cannot be included. So again, a round bracket next to 0, upturned U, so union, and then from 0 onwards all the way to infinity, any value can be in the domain of the newly formed composite function. Finally, we go over the process of decomposing a composed function. In other words, writing a function as a composition, which means we are given a composed function, we're given a composition, in this case h of x equals square root over x squared plus 5. We have to decompose it. We want to write it as two functions, f of x and g of x. All right, so the way to go about it is look at what the operation here is. It's square root over x squared plus 5. So we have taken an expression and put it under the square root function. So here the primary function is, okay, the primary function is square root function. Okay, the square root function, which is f of x equals square root of x, right? That's the primary function. And then we have replaced x with, if you look at the composite function, we have replaced x with x squared plus 5. So we'll make whatever is under the radical, under the square root sign, as the other function, which is the input function into f of x, into this x, which is a part of f of x. So the way we write it is g of x equals just what is inside the or what is under the radical. So that's x squared plus 5. Okay, and that's what they have written here. All right, that's the answer they got to, but I just wanted to explain how they came up with this.